you go.
Okay, so thanks very much, Marco. It's a pleasure to be part of this conference as a prior Tony Nordrat student and share the time with some of my former graduate student colleagues. So today I'm presenting on behalf of Ero Copper on the deposits in the Curaca Valley. Now I'm trying to advance and it's not advancing. Okay, so given that this is I'm presenting on behalf of Ero and the team at Ero Copper, I have to start with obligatory cautionary statements and also a disclaimer, which basically says that you should be cautious about everything that I say. So Ero Copper was formed about 4 years ago, almost exactly 4 years ago, to acquire the assets in the Curaca Valley. And it started operations immediately again in Pilar, and then brought Vermelhos to production shortly thereafter. And since then, they have made 5 additional discoveries in the valley, shown here on the bottom of this slide here, to add to the reserves and the resources. And you can see the share price backed on this slide. The cumulative effect of all that work is the addition of 430,000 tons of additional copper between 2017 and 2019, and there'll be another release coming up shortly. And that obviously involved a huge amount of work, 650 kilometers to be precise, of drilling over that period. So that's a huge amount of additional data and observations that have been made as a result of that drilling. Moving to the geology, the Curaca Valley is located in the northern part of the São Francisco craton, in this area up here, and you can see the 3 main deposits I'll show you in a minute highlighted there. The Curaca Valley is part of the Itabuna Salvador Curaçao belt, which is a belt of rocks sandwiched between 2 Archean blocks to the east and the west. The Curaçao Valley rocks were deformed and metamorphosed between about 2.3 and 2.09 billion years. And peak metamorphism was around 2.1 at above 800 degrees centigrade and greater than 70 kilobars of pressure. Following that peak metamorphism, there was a large mafic complex in place just on the east side of the Curaçao Valley at Jacariki, and a large cyanide body 100 kilometers north-south in dimensions to Itabaiuna. And then at around 2.05, we had in place the granites, pegmatites, and the critical suite of mafic and ultramafic intrusions that I'm going to be talking about today. I would like to note that although these dates are defined by reasonable geochronology, there's only a small amount of data, so there is still some room to improve the amount of information on the timing and so on. But I'd also note that that 2.09 period is, of course, a rather interesting one, as was illustrated by Marco a couple of weeks ago. So we'll zero in on the Curaca Valley. On the right-hand side of this slide here, we see the Curaca Valley, and the green little dots all through here are all the mafic and ultramafic intrusions that I'm going to be talking about. Pilar is the main deposit, the original Caraíba area in the south, and Vermelhos that I mentioned previously is up in the north. Sorboon is a previous producer. So the mafic ultramafic intrusions post-date the deformation in the gneissic host rocks. The suite is widely variable from peridotite through to a north site, but orthoperoxenites are dominant, and they're the most important in terms of host for mineralization. Although mineralization also occurs in some of the other mafic ultramafic rocks and in the gneissic ore rocks. Mineralization is copper dominant, although there are concentrations of nickel, cobalt, platinum, palladium, and gold, which I will talk about. Mineralization is disseminated to massive chalcopyrite and a lot of bornite, and the bornite has been noted by previous workers as unusual. There is local pyrrhotite, pegmatite chalcopyrite ore that's more typical of magmatic styles of mineralization, and there are abundant spinels and oxides, chromite, magnetite, etc. The low nickel copper ratio, low sulfur selenium ratio, the amount of bornite, the amount of oxide have all been regarded as unusual for magmatic sulfides, and some have suggested therefore that these deposits may be the deep roots of IOCG deposits. So very compatible with some of the ideas that were just discussed in the last 2 talks. And that's supported to some extent by the abundance of phlogopite associated with the orthoperoxenites and mineralization, local carbonate, and some potassium, sodium, calcium alteration, which is proximal to mineralization and occurs in regional structures. So we'll zero in and take a look at the rocks. On the right-hand side now is the same map, but in this case, the yellow dots all through here are the mafic, ultramafic rocks, intrusions of interest. In the picture on the right-hand side here, you can see one of these intrusions cutting clearly across the gneissic fabric. And on the other 2 pictures, you can see some of the other textural varieties, breccias in some some of these Mafic-ultramatic rocks. You can see more traditional cumulates here, and then some fine-grained rocks, which are a little enigmatic as to whether they're part of this suite or whether they are part of the original gneissic assemblage rocks. On the edge of this mafic intrusion, you can see this dark black color, perhaps. That's this phlogopite-rich alteration, which often contains apatite and zircon. So again, a little bit of similarities to the previous talk. This slide here shows the range of compositions of some of the intrusive rocks, from the most mafic brilliantitic through to more plagioclase-rich rocks. This is not only varying composition, but varying textural characteristics. These rocks have been interpreted to be of mantle derivation, although some have suggested some alkaline character, some crustal potential contribution, and they've even been suggested to be restites from partial melting. They have relatively elevated light rare earth elements, and they are somewhat hydrous. The mineral chemistry is variable. It's quite evolved. The orthopyroxene compositions are quite evolved. Plagioclase variable and quite evolved. And there's certainly a suggestion that the high pressure temperature conditions, again, above 800 degrees, above 7 kilobars, may be reflected in the compositions of these minerals. A number of workers have compared the Caraíba district, the Curaçao Valley deposits, to the Okiep district in South Africa. But to my knowledge, Wolfgang Meyer and Sarah Jane Barnes, who are obviously involved in this conference, are the only two people who've worked on both of them. So I'll acknowledge them up front. A couple more pictures here to show the relationship of mineralization and orthopyroxenite. On the left, top left here, we have an orthopyroxene in contact with the gneissic rocks, and you can see mineralization apparently leaking down into the gneissic rocks. Over here, further over, we see again chalcopyrite-rich mineralization in the orthopyroxenite, again moving into the gneissic rocks. And here we can see a close-up and drill core across the bottom with orthopyroxenite on the left into gneissic rocks, with bornite and chalcopyrite dominant mineralization heading through in veins and networks through the gneissic rocks. And on the right, a close-up of that, the contact between the gneiss and the orthopyroxenite, showing clearly that the orthopyroxenite is discordant. We'll look at a couple of cross sections. On the left is a cross section through Pilar. That's the deposit in the southern part of the district down here. You can see that Pilar is a very deep, attenuated series of lenses of deposits with an unusual sort of structural character here. The current focus of exploration now is down in the deepest part of the deposit, some 1,500 meters below surface. You can also see an association here with pegmatitic intrusions in what may be some structural feature. On the right is the Vermelhos deposit. Again, we have pegmatitic intrusions and a structural zone with alteration in it, containing some mineralization, and then some mineralization in pods here, which appear to sit within the fabric, within the gneissic fabric. We'll zero in and look a little more closely at Toboggan here. Here's a close-up of part of Toboggan showing one of the recent drill holes through it, and indicating the spectacular grades that are associated with this style of mineralization. You may or may not be able to read it, but the pink there has an intersection of 31.5 meters of 8.7.2% copper, and there's additional mineralization below it. Importantly also, we also see some nickel in Vermelhos. So here are some nickel values up to 4.3% nickel. Take a look at some of the mineralization here. This is the copper mineralization, 3 pieces of core with the copper mineralization, showing what appears to be magmatic style textures ranging from disseminated to net textured and coagulated, more massive chalcopyrite. You can also see in this apparent clast of massive sulfide, a rim around it, which is dominantly a spinel. A suggestion of layering, perhaps, in some of these rocks here. If we go up onto the top left here, I'll zero in on that for you. There, you can see that we have disseminated or interstitial sulfide, in this case, chalcopyrite and bornite, but interestingly enough, they seem separate from each other, with bornite concentrations in some places and chalcopyrite concentrations in others. And that obviously causes some problems for interpretation in terms of a magmatic sulfides model. The 2 photos below are from Pilar, down here, and both of those show unusual chalcopyrite bornite intergrowths and complex textures. And you may be able to see along the bottom of the lower picture there, a little white rim, which is the carbonate rim that occurs along the edge of some of the sulfides. Breccias are very common in this deposit. So we have breccias with host rocks and sulfide breccias. In this case, you can see clasts within the sulfide and sulfide segregations moving out with clasts into some of the wall rocks. Over here on the far right, we have a very interesting texture which appear to be globules of sulfide within the orthopyroxenate host. I mentioned phlogopite and carbonate. This is intense phlogopite replacement of orthopyroxenate over here on the left side. This is the rock that would also contain some apatite and zircon. In the middle here, we see a sulfide vein with phlogopite forming a selvage and being cut by phlogopite. And then in the center here, we have some very coarse phlogopite, which appears to be in equilibrium with chalcopyrite. And the pictures over here on the right show this carbonate rim going around some of the sulfide segregations, and even extending out through this vein here, which is chalcopyrite into bornite, and then carbonate, a carbonate vein extending from that apparent sulfide vein. And finally, the other styles of alteration, potassic rich and sodic rich, you can see some of the feldspar developed in these rocks, in the gneissic rocks here, and again in these rocks, and this is an albite rich zone of alteration here. So some alteration, which again supports or can support a potential connection to IOCG mineralization. And lastly, an example of garnet-rich alteration, or garnet growth, I should say, at Vermelhos in here and in here. And in this case, you can see interstitial sulfides within the garnet and interstitial phlogopite here, again, within the garnet at Vermelhos. So just a few quick pictures of close-ups of some of the sulfide textures. The first one slide here comes from Pilar. These are all samples from Pilar at various scales. You can see on the left, chalcopyrite-bornite relationships in veins and more concentrated segregations, and then the disseminator interstitial sulfide, which varies in composition from chalcopyrite-rich to bornite-rich. In the middle here, we have bornite surrounded by magnetite. Magnetite is the dominant oxide phase at Pilar. The picture below, this white grain is probable melanite. That would be the nickel telluride. And on the top right, we have some digenite chalcocite at the interface between bornite, chalcopyrite, and magnetite. And finally, bottom right, phlogopite, showing a sort of fabric that may suggest some deformation post-phlogopite formation. We go to Vermelhos, again, similar textures now, some massive chalcopyrite, bornite chalcopyrite here, and in this case, the appearance of pentandites, a significant amount of pentandite, not unlike some of the textures that were just shown in the previous talk. In this case, the spinel phase, the dominant spinel phase at Vermelhos is chromite. We see over here some bornite chalcopyrite intergrowths. Again, this phlogopite texture suggesting some degree of deformation and some melanite crystals. And finally, we'll go to Siriema. Siriema is a new discovery close to Vermelhos, and it has the most magmatic sulfide-like mineralogy. However, the mineralization in this case is hosted in part, at least, in the gneissic wall rocks. You can see here, down here, that we have phlogopite within the sulfide, but in the central picture here, the most interesting textures is a loop texture of pentandite within pyrrhotite, and you can see this close-up here of the pentandite forming around grains of pyrrhotite. And lastly, in the bottom right here, we have a texture that looks almost like a symplectite intergrowth between sulfide chromite and the silicate minerals. So I mentioned that we were at Siriema. This is the Siriema deposit that we were just looking at, which is the most nickel-rich discovery so far. And this is Vermelhos over here and the Tubagon zone that I drew attention to. And pretty much all of the area beneath these deposits is open for exploration. And just to illustrate again the importance of Siriema, this is a couple of intersections here through this drill core. On the left here, a meter of 3% copper and 1.2 nickel, but over here on the right, in forming these veins and segregations, we have 1.4%, 1.46 meters of 7.5% copper and 4.7% nickel. It's a very interesting mineralization. So just to summarize quickly the sulfide mineralogy, I've mentioned bornite chalcopyrite, sometimes with digenite chalcocite, and then a more traditional, if you like, magmatic assemblage of pyrrhotite pentandite chalcopyrite. We have a lot of complex oxides and spinels. We have a lot of complicated textures, both in oxides and in spinels, and these are not uniform nor well understood at this point. We have other trace sulfides present, melanite and probably others. We have disseminated net textured massive sulfides, which are indicative of magmatic textures, and a lot of breccias. However, we also have the important presence of the phlogopite with the carbonate rims around some of the sulfide segregations. It's copper dominant, but again, we do have nickel and cobalt. And we have some interesting concentrations here of some of the other elements, silver, gold, palladium, and platinum. And I'd draw your attention particularly to tellurium. Tellurium ranges from less than 0.1 to 50 ppm, but goes all the way up to 300 ppm and correlates closely with copper, nickel, cobalt, and chromium. So in conclusion, we believe the Curaçao Valley is a major metallogenic event. It's around 2.05, perhaps 2.09 to 2.04, remains to be defined exactly. It's associated with Mafic-ultramatic suite. We have evidence for what we believe is magmatic sulfides. And these were placed with the orthopyroxenates and other Mafic-ultramatic rocks post-major deformation, but they do show some structural influence. It's copper dominant. There's three potential ways to explain that copper dominance. We could have a source region control, a low degree of partial melts, as suggested by Dave Howell and Darrell Blanks. It could involve magmatic fractionation, and it could also involve sulfide fractionation, particularly sulfide fractionation under the high pressure temperature conditions, which might explain, along with some of the hydrothermal activity, the distribution of these elements. We believe the chances are that there's some combination of all of these mechanisms involved in these deposits. The phlogopite-carbonate suggests that the melts were hydrous and probably CO2 rich, and they may have played a role in, again, in the movement of concentration of the sulfides. We do have these other intrusive rocks of the same age, granites, cyanites, and pegmatites, and they may be producing some of this potassium, sodium, calcium alteration, and there may be some relationship, we're not certain, to mineralization. And again, that's a potential link to ICG. And lastly, there's clearly potential for significant new resources and discoveries in this major district, but we have many questions to answer. Thanks very much.